Welcome to this video on revision worksheet 12. So this revision worksheet contained 3 questions, all based on probability and statistics. So the first question came from 2015 paper 2, section A, and it was question 2. Question 2 then came from the 2015 sample paper, and Again, it was from section 8, it was question 1, and then the third final question was 2013, paper 2, section 8, question 2. So they're all based on paper 2 questions, and they're all based on the 25 mark questions. So let's take a look. So question 1, a survey of 100 shoppers randomly selected from a large number of Saturday supermarket shoppers showed that the mean shopping spend was 1945 and the standard deviation of this sample was 2073. Now, this is hugely important. They've straight away said, oh, there was 100 people. That means that they're not talking about the full population. They're not talking about all the shoppers. They didn't ask all the shoppers. They only asked 100 of them. So this 100 here is really, really important. It's telling us N. Sorry, my pen's not working now. So it's telling us N because we have a sample. And what that means for us is when we get into this mean shopping spend, this is the mean of the sample. So you need to know the difference between the mean of the sample and the mean of a population. So for the mean of a sample, we use X bar. Now, you may have used both a junior set X bar and mu interchangeably, and I know that can cause some confusion. However, what I will say is, if you do not have the correct symbols here, you will incorrectly put it into your formula and you'll get the wrong answer. So you need to be able to label this correctly. So when we're talking about the mean of a sample, we're doing X bar. When we're doing the mean of a population, or if they don't mention anything about sample, we're using the mu, that Greek letter mu. So the standard deviation of the sample, the standard deviation is slightly more straightforward because we're always going to take that the standard deviation of the sample and the population is always the same. So we can always just write this as our sigma. We're not going to get any more complicated than that. So it said find the 95% confidence interval for the mean amount spent in the supermarket that Saturday. Okay, so let's take a look. 95% confidence. So we're always going to be dealing with 95% confidence. The only other thing we might see is 5% significance, and they both give us the same number, which is 1.96. Okay, that's coming from our standard normal tables, but you need to know that. So there is a little formula that can help us to do this. So this is one that I would advise that you learn off. So to get the confidence interval, it's X bar plus or minus 1.96 sigma over root n. So basically that's saying is the mean here is not correct because it's only a sample. So we know if we take a sample, we're not getting a full accuracy like we would if we asked the whole population. So we take that mean of the sample, which is a good starting point, but then we have to account for the error. And that sigma over root n is actually called the standard error of the mean. So we take the 1.96, which is linked to the 95% confidence, and we multiply it by the standard error of the mean. So that's where that formula comes from, and I would advise you to know that formula. So working with that, we basically get 90.45 minus, I'm going to do the smaller one first. The smaller one will always be the negative. Over, so that's 20.76 all over the square root of 100. Okay, so that's the lower band. And then there's the upper band, which is 90.45 plus 1.96 by 20.76 all over root 100. So the actual mean sits somewhere in there, and that's mu, and that's the mean of the population. This is the difference between the mu and the X bar. So mu sits somewhere in there. So working that out, this works out here at 86.39, and mu sits somewhere in between there and 94.51. So you can see that the mean of 90.45, it wasn't exact. We couldn't say that that is where our actual mean is. It's not the same as the population. As we do more and more samples, we might be able to say that, but for now we can just use it to help us create a confidence interval. So we know with 95% certainty, or we can say 95% of the time, that the actual mean of the whole population, so the mean amount spent in a supermarket on this Saturday, was between 86.39 and 94.51. So part B then says the supermarket has claimed that the mean amount spent by shoppers is 94. Based on the survey, test the supermarket's claim using a 5% level of significance. Clearly state your null hypothesis, your alternative hypothesis, and your conclusion. So this is hypothesis testing. So we always start that off the same. We start off with our null hypothesis. So a great way to remember your null hypothesis, it's always mu equals. So they've told us that the mean is equal to €94. Okay? And what I would advise you to do is not just write it as in the mathematical way. I would always start in the mathematical way, but put it back into words. By doing that, it will help you with your conclusion, because often we see that the null hypothesis is not necessarily agreeing with what was initially stated by, it wasn't the thing that, in this case, they've said the mean amount is 94. Yes, okay, our null hypothesis is what they said, but that's not always the case. So what we would say here, so the mean amount spent by shoppers on a Saturday is 94. That's our null hypothesis. So our alternative hypothesis H1 then is mu does not equal 94. So we have to cover all eventualities. So mu is not 94. So we say again the same thing. The mean amount spent by shoppers on a Saturday is not, and that's important, 94. Okay. So this here is our null hypothesis and alternative hypothesis. We then need to test it. Now, there's two ways to test it. We can use our Z-score, calculating our Z-score, working through that. That's absolutely fine to do. There is examples of all of those done in other videos, so I'm going to work with this question like we would if this was in an exam. If it was in an exam, the first part, so part A of this question, asks us to get the 95% confidence interval. And I'm just going to write it down here. So the 95% confidence interval from the previous part basically said, well, 86.39. So maybe it's somewhere 94.51. So mu is somewhere in there. Okay. So we know, since mu is somewhere in there, if the mu they've given us does sit in there, then we can accept the null hypothesis. If it does not sit in there, then we would reject the null hypothesis. So what we have here is 94. Mu is equal to 94 is what they've given us. So 94 does sit. So what we would say is 94 does sit in the above 95% confidence interval. Okay. Therefore, we accept the null hypothesis. Or we can fail to reject. Okay. Now, that's about our hypothesis. However, our conclusion then needs to link back to the question. Okay, and this is the bit that I think a lot of people are missing. It's the idea of the conclusion. just finishing accept or reject is not necessarily the conclusion. You have to link it back. Well, what we can say is, we can say the supermarket, or whoever, in this case it's a supermarket, claim that the mean amount spent, so we're going back to this statement, by shoppers on a Saturday is €94 is correct. So that's our conclusion. Now, like I said, you can work out your z-score, and if you're working with your z-score, what we do is we take that 94 and we basically standardize it. We're going to standardize it against, well, we're actually going to standardize the 90.45 against the mean of 94. And we use the one sample z-test is what it's called on page 35. We work out a z-score. And what we would say then is if that z-score lies between minus 1.96 and 1.96, we would accept. Okay, similar idea. So it's another interval, but it's a z-score interval as opposed to a mean interval. So like I said, I'm doing this question like we would approach it if it was an exam question. On the solutions I've uploaded, I've also calculated the z-score. It works out as minus 1.71, and this question has been done a number of times. So like I said, I would advise you to kind of work with what you have, but some people do love going that z-score route regardless of the question. So the p-value of the test you performed in part B above, and explain what this value represents in the context of the question. So given that I've used a confidence interval, the p-value actually does need the z-score. So the first thing we're going to work out is say, well, look, let's see what the z-score is here. So like I said, we're going to work here on from page 35, and it's called the one sample z-test. And its z is equal to x bar minus mu all over sigma over root n. So it's kind of accounting for the fact it's a sample. So from our question, we can work out our x bar is 90.45. Our mu from the previous part was 94. All over 20.73. All over the square root of 100. When I work that out, it's minus 1.71. So that's our z-score. Since that's sat between minus 1.96 and 1.96, we would have accepted. That would have been for part B. But here we want to figure out the p-value. So the p-value is twice the probability that z is less than this number here. Okay. So working out the probability that z is less than minus 1.71, that is 1 minus the probability that z is less than 1.71. Again, if this is something you're not familiar with, do go back over those videos to go back through it, to revise. There's a few different videos linked in the description here which will show you how to work through z-scores and the idea of converting from a negative to a positive, and how we can use the idea of symmetry and so on. So this works out as 0.0436. So the p-value is twice 0.0436, which works out as 0.0872, which works out at 8.72%. Okay, so that's my p-value. Now, what does that mean in the context of the question? Well, we're comparing the p-value to 5% level of significance. significance. So 8.72% is greater than 5% level of significance. Therefore, we accept the null hypothesis. Too many U's in there. So this would be another method that we would use for the null hypothesis, although we would only use it if asked. So what this means is if the mean amount spent really was €94, then the probability that the sample mean will be 90.45 by chance is 8.72. Because that's bigger than the 5% level of significance, we would accept the null hypothesis. So let me put this down for you. So if the mean amount spent was actually or really €94, then the probability that the sample mean, remember our X bar, will be 90.45 by chance is 8.72%. And because that's bigger, so then we're linking it back, because that 8.72 is greater than 5% level of significance, that's why we accept the null hypothesis. So question 2 then, a survey of 50 Leaving Cert candidates. Now, as soon as you see a number given, like 50 Leaving Cert candidates, 100 shoppers, we should be straight away thinking, okay, we're being asked to deal with a sample here. We're not dealing with the population. So this 50 represents our N. So they're randomly selected from the Dublin region, and it has a mean mark of 374. So again, this mean mark is X bar, and the standard deviation is 45. So that's straightforward. That's just our mu. Sorry, that's just our sigma. So find the 95% confidence interval of the mean mark in the subject in the Dublin region. So just like before, we have our formula. We have X bar plus or minus 1.96 because it's 95% confidence. 1.96 sigma over root n. So we have 374 minus, remember we're always doing our minus first because it's going to be the smaller number, 45 all over the square root of 50. It's between 374 plus 1.96, 45 over root 50. So when we work those out, we get 361.527 and 386.473. So that is our confidence interval. But then they asked us to interpret this interval. So we can say with 95% confidence or 95% certainty, or we can say 95% of the time confidence that the mean mark in the Dublin region lies between those two values. So I'm going to say lies in the above interval. So the mean mark in the subject for all Leaving Cert candidates in 2014 is 385 and the standard deviation is 45. John suggests that the mean mark in the Dublin region is not the same as the whole country. Test this hypothesis using a 5% level of significance. Clearly state your null hypothesis and your alternative hypothesis. So the 385 is for all candidates, so that's our mu. So our null hypothesis, we always start off with our null hypothesis, and that's mu equals 385. Now, this is a really important one to put it in words because you might notice that John suggested the mean mark is not the same as the whole country. The fact that John says that doesn't impact on our null hypothesis. Our null hypothesis is always mu equals. That's what we work with. We always work with it being mu equals, and the alternative hypothesis mu does not equal. However, it will affect our conclusion at the end. So what we have here is the mean mark in the Dublin region is the same as the whole country. Our alternative hypothesis then, mu does not equal 385. So the mean mark in the Dublin region is not the same as the whole country. Okay. So then we have again our confidence interval. However, this time just to show you, I'm going to use the z-score method. So I'm going to take the idea of z is equal to x bar minus mu all over sigma over root n. And for us, that's going to work out as, so our x bar from the previous part was 374 minus 385, standard deviation is 45 all over root 50. So that works out as minus 1.73. So that's our z-score, 1.73. Now, to decide whether we accept or reject, we use the idea of minus 1.96 and plus 1.96. That is where our z sits between, if it is a 5% level of significance. So what we'll say is, since z equal to minus 1.73 sits in the above interval, we accept the null hypothesis. Now, 385 also sat in the confidence interval from part A, so we would have also accepted the null hypothesis there. The last part now is to come up with our conclusion. And our conclusion is important, especially here. So we've accepted the null hypothesis, so the mean mark in Dublin region is the same as the whole country. However, we will have to conclude that John's suggestion, and you can fill it in, I'm just saving time now, not filling it in. You say his suggestion that the mean mark in the Dublin region is not the same as the whole country, we would say is not correct. So we link it back what John says. So what we've been told, or what is being suggested in the question, or what is being claimed in the question, does not necessarily link to that null hypothesis. So the null hypothesis is always mu equals. So my advice on dealing with questions like this, always write down null hypothesis mu equals whatever and then put it in words. Alternative hypothesis mu does not equal whatever and then put it in words, and then it's much easier to see your conclusion at the end. So question 3, a random variable x follows a normal distribution with a mean of 60 and standard deviation of 5. So here we're talking about mu, we're not talking about any kind of sample, and standard deviation of sigma. Here we're going to let x equal 68 and we're going to standardize it. Standardizing it using the formula on page 34 of your log tables. It's called the standardizing formula, and it's z is equal to x minus mu all over sigma. So z is equal to 68 minus 60 all over 5, which is 8 over 5, but we need these all as decimals, which gives us 1.6. So this is the probability that x is less than or equal to 68. It's the same as the probability of z is less than or equal to 1.6. So we rewrite it. Instead of x, we're working with our z, our standardized form. And instead of 68, we've converted that 68 to 1.6 using the formula. Then we go to our log tables again on page 36 and 37, and we're looking at 1.6. 1.6 appears on page 37. So this gives us 0.9452, which can also be written as 94.52%. So it basically means that in our standard, in our normal distribution, if I pick 1.6, 94% of the data lies below that. That's my standard normal, and then just my normal, if that was 68, 94 lies below it. So now we're looking at the probability that x lies between 52 and 68. So the first thing we need to do is we're going to convert. So you can do it either way. You can convert it first, or you can rewrite it first. I'm going to rewrite it first. So this is the probability that x is less than or equal to 68 minus the probability that z is less than or equal to 52. Apologies, that should be x. Now, we've already worked this out. This is 94 point, I'm going to go back to my decimals. So this is 0.9452 minus. Now, we haven't figured out what the probability that x is less than 52 is, so we have to again work with our formula like we did in the last time. X minus mu all over sigma, and this time my x is 52, so I have 52 minus 60 all over 5, which is minus 8 over 5, which is minus 1.6. So that's the probability that z is less than or equal to minus 1.6. Now we can't work directly with a negative number in our tables, so what we have to do instead is we change it to a positive. This is all covered in the videos linked in the description. So 0.9452 minus 1 minus 0.9452. And working all that out, 0.8904, which is 89.04%. So you can write it either way. So the heights of a certain type of plant when ready to harvest are known to be normally distributed with the mean of mu. A company tests the effect of 3 different growth hormones on this type of plant. The 3 hormones were used on a different large sample of crops. After applying each hormone, it was found that the heights of the plants in the sample were still normally distributed. Okay, so that's important. The diagrams A, B, and C on the next page show that the expected distribution of the heights of the plant at harvest time without using the hormones. The effect of the plant growth on each of the hormones is described on the next page. Sketch on each of the diagram the new distribution to show the effect of the hormone. So we know that when we sketch it, it's still going to be normally distributed. That's important. It's not going to be skewed in some way. So hormone A, the effect of hormone A is that it increases all the heights. It increases the height of all the plants. So all the plants get taller. So remember what this means is, on this diagram, down here is the height, and here is the number of plants. So if they all got a bit taller, there's suddenly, if there was only one here, it's not going to exist anymore. It's going to have got taller. So effectively what happens is this whole curve shifts to the right. So you end up with something like this. So still normally distributed, but my mu has now shifted Okay, so that's my new mu, because the whole thing has shifted then to the right. Now, that should look a bit more symmetrical than that. It is very hard to draw on this. But they're not looking for, you know, a huge amount of accuracy. Yes, they want to see it as accurate as you can draw, but you are still drawing it freehand. Really what they're trying to see is, did you get the idea of it shifting to the right? So hormone B then, it says the effect of hormone B was to reduce the number of really small plants and really tall plants. The mean was unchanged. So what has happened here is, again, remember these are our heights. So if I have my height, sorry no. If I have my heights here, these are my small ones and these are my really tall ones. So they effectively disappear. Okay? But the same number of plants. So effectively what happens is the mean is still coming up here, but it doesn't go as far out. So we get this idea of a skinnier distribution. Okay? But my mean is still there. So it's kind of brought up the center. It's made it much more narrow, a taller, skinnier version here. And hormone C, the effect of hormone C was to increase the number of small plants and the number of tall plants, and the mean was unchanged. So this time we end up with a slightly fatter but lower shaped curve. So something like this. Again, we're looking for it to be as symmetrical as possible. So we have more here at each end. So notice how this bit has got bigger. But the number of plants in the middle has reduced. However, the mean has stayed the same. The mean hasn't changed. So the mean has only changed in our first part here. So that's it then. So there are 3 sketches.